Hello and welcome to NHP's live webinar on safety logic devices and applications. My name is Daniel Nathanson. I'm a commercial engineer for NHP Electrical Engineering, specializing in automation and integration products and solutions, and also a TUV Rhineland accredited functional safety engineer. This is just one in a series of webinars created to showcase NHP's smart devices, powered by smart distribution and embedding smart safety into operational processes, providing our customers with better visibility into processes, data, and analytics. In this session, we will specifically be looking at safety monitoring relays, their application, special functions, and why they should be used with respect to the machine safety standards. This session also continues on a series of live and on-demand webinars on other machine safety topics. If you haven't had a chance to view some of these, I would highly recommend you head over to the NHP YouTube channel to view them after this webinar. This webinar will also be recorded and uploaded to the NHP YouTube channel. Some of the key topics we'll cover in this session include typical fault lists and exclusions, diagnostic coverage or DC and its importance in the safety control system, fault monitoring and detection, and safety monitoring relay logic and some examples. Please use the chat function to submit any questions and our expert moderators will answer as we go through. Time permitting, we can go through any remaining questions at the conclusion of this webinar. Safety monitoring relays are special logic devices used within machine safety applications to perform various different tasks. They range from the most basic single functions like discrete on-off for emergency stop or interlocking, to more advanced functions like time delay and speed monitoring for guard locking functions. Often also called a safety relay, the safety monitoring relay's main function in a safety control system is not only to provide logic for safety functions, but also to perform the necessary fault monitoring and diagnostics to maintain safety integrity. This makes them a critical component in any high-risk safety application where diagnostics are essential. But how do we know when our safety control system requires diagnostics? If we only have a basic on-off logic, then surely we can do without. Well, we must always establish the requirements of our safety application by going back to the essentials. Recall our previous Safety Essentials Part 1 session, which if you haven't seen yet, I highly recommend watching after this webinar. First off, identify the hazards associated with the machine: crushing, cutting, impact, pinch points, etc., or other non-mechanical hazards like noise, heat, and radiation. Perform a risk assessment on the hazards, take into account the processes and the people involved, and determine the residual risk and how best to reduce it. Appoint the safety functions which will be used to reduce the risk. This could be interlocking of guards, speed monitoring, or even requiring a manual reset on the safety control system before restarting. Determine the required safety category, performance, or safety integrity level for your safety control system. Use the safety of machinery standards to guide you through the processes and requirements. Design your safety control system to not only perform the necessary safety functions, but also meet the required safety performance level or integrity. And verify that your safety control system and the parts that you're using meet the requirements for the safety performance level required. Then validate the system to ensure that it works correctly in all expected operations, so normal, maintenance, and faulted states. It may be that your required safety control system needs to have fault monitoring and diagnostics. This is why you must go through the process to determine this, and the standards will help you. In our Safety Essentials series, we covered the basics on qualitative and quantitative standards for safety of machinery. If we take the quantitative standard for performance level, which is AS/NZS 4024 Part 1503, we have a simplistic method of determining the fundamental requirements for our required performance level. In each column of this chart, we have a combination of safety category, mean time to failure, and DC, diagnostic coverage. And depending on these combinations is the resultant performance level. So for example, if we require the highest level of safety in terms of reliability and performance for our safety control system, performance level E, we have the option of two columns on the far right. We can design a category 3 with high mean time to dangerous failure and medium diagnostic coverage, or we can design a category 4 system with high diagnostic coverage. The main point here is that we have this element called diagnostic coverage, which we should explore a bit deeper. Note that performance level D and E requires at least some level of DC. And if you're looking at categories only, we find the same requirements for anything category 2 and above. We get DC by monitoring for dangerous faults. This is where safety monitoring relays become a useful tool for achieving this. When we are talking about fault monitoring, we need to know what kind of faults we should be considering in the first place. If a fault occurs, is it of any consequence? Is the fault detectable? Is the fault likely to occur at all? We should be looking at every component which contributes to the safety control system, but what is reasonably foreseeable? Conductors or cabling is very much an essential component of the safety control system. It's often overlooked, and I can assure you from my own experience, it's one of the most common faults associated with the failure of the safety control system. Consider faults with the wiring. Loose connections, improperly stripped insulation, routing along power wiring, among many others. Faults that can arise from improper wiring practices include short circuit between conductors, open circuits, and induced voltages. However, we may be able to exclude some of these faults under some circumstances, because the likelihood of them occurring is so remote that we don't need to consider them. In AS 4024 Part 1502, which is the standard for validation of safety control systems, it provides useful examples of faults in the various components in all types of control systems. That includes pneumatic, hydraulic, mechanical, and electrical. It also provides examples of basic and well-tried safety principles and components, and provides rationale for the exclusion of some faults. Annex D in particular looks at electrical systems. Let's take a look at some examples that it provides. In conductors and cables, we see some faults that we should be considering. These are not an exhaustive list, rather a sample of what you'll find in the standards. Let's consider the fault of a short circuit between any two conductors. We can justify the exclusion of this fault from occurring by one or more of the following. The conductors in question are permanently connected or fixed and protected against external damage by, for example, cable ducting, armoring, etc., or running separate multi-core cables, or the cables are enclosed within an electrical enclosure, which, if we see the remarks, both conductor and enclosure meet the appropriate requirements in AS 60204 Part 1, which is the general requirements for electrical equipment used in the safety of machinery. I should now mention that this standard has been updated and incorporated into the rest of the AS NZS 4024 series. It's under Part 1204. Or we run individually shielded conductors with shielded earth. One or more of these measures significantly reduces the risk of a short circuit occurring between conductors in the safety control circuit, enough so that we don't have to concern ourselves with any further monitoring for these faults. Thus, we have excluded them. However, some faults cannot be excluded. The open circuit of any conductor has no rationale for excluding this fault. Therefore, this is a fault that we must consider and monitor with the diagnostic capabilities of our safety control circuit. Let's also look at the faults which may occur in an electromechanical position switch, like a limit switch or a tongue interlock, for example. Contacts will not close. There is no fault exclusion for this. Therefore, we must consider that this fault may occur and monitor for it, and ensure that this fault does not result in the loss of safety. Contacts will not open. This one does have a potential fault exclusion. We can consider that the likelihood of the contacts not opening on demand isn't significant enough to warrant monitoring for, provided that the contacts are in accordance with AS 60947.5.1 Annex K. If you're not familiar with the standard, and I will forgive you, this is the one that describes the requirements for electromechanical control circuit devices. Annex K in particular describes the supplementary requirements for direct opening action. If you've seen in our Safety Essentials series and also in the previous session on interlock switches, direct opening action is one of those well-tried safety principles which make components safe, which it relies on direct mechanical action to force the contacts open rather than reliance on springs or other non-resilient means. On this topic of this standard, if the position switch is constructed to this standard, we can exclude the possibility of faults occurring as a result of short circuit between adjacent contacts, provided, as per the remark, that the conductive parts which become loose should not be able to bridge the insulation between contacts. This would require special construction of the terminals and proper preparation of the conductor before fixing. So, for example, appropriate stripping of the insulation, correctly sized ferrules, and so on. When it comes to electromechanical output devices like contactors and relays, we can't rely on direct opening action to save us from faults occurring, because these are electrically actuated, not mechanical. So naturally, some faults we just simply cannot exclude from occurring, so we have to monitor for them. Some of the faults in question are those related to mechanical failures of the device. For example, the contacts remain unintendedly in the energized or de-energized position, or the contacts fail to open or close on demand. These could be attributed to faults in the wiring, induced voltage by nearby conductors holding the coils energized, ingress into the contact mechanism, or stuck contacts due to oxidation or overload. We need some way to detect these faults and account for them, as it is possible that they may occur eventually during the expected lifetime of the machine. There are some faults which we can exclude, but these are again primarily attributed to wiring faults, which are resolved by appropriate construction of the device and its terminals, and adhering to appropriate wiring practices like observing creepage and clearance distances. So we've identified several faults which could lead to the loss of safety in our safety control system. How can these be detected, if at all? How much does this monitoring contribute to the integrity of our safety control system? This is what diagnostic coverage is for and what it means specifically. AS 61508 is the standard series which provides much of the framework for the use of electrical and electronic devices for safety control systems, and is used in the machine safety as well as the process safety world. It's a multi-part series, of which part 4 is the list of all definitions and abbreviations, and it is here where DC or diagnostic coverage is defined. It is DC is the fraction or percentage of dangerous failures detected by automatic diagnostic tests. In essence, it's the total number of dangerous failures which are detected by the diagnostics divided by the total number of dangerous failures in a given sample. So say we have a sample of some number of contactors and we cycle them on and off continuously until they fail. How many of those failures do we consider to be dangerous given our application, which in machine safety is typically the contacts failing to open? And then what percentage of those dangerous failures can we automatically detect using our safety control system? This is our diagnostic coverage. If we look back at our chart for performance level, we can see that DC is given in 4 ranges, which is denoted by none, low, medium, and high. And these are given in percentages per the definition of DC from the standards. So a DC of high is anything greater than 99%. That means that more than 99% of dangerous failures we can detect, whereas a DC of none is less than 60%. Consider this. Even if we detect more than half of our dangerous failures, this is still a failure of the level of diagnostics to perform. While it's nice that most of our dangerous failures are detected, it's not enough. It may as well be none. So for high-risk applications, we need to be able to detect as many dangerous failures as possible to ensure the integrity of our safety control system. Recall that for performance level E, we have 2 columns to choose from. Category 3 with medium DC, and this does require a very high mean time to dangerous failure, or category 4 with high DC. The former requires at least 90% of dangerous failures to be detected, and the latter at least 99%. This is a serious level of diagnostics required. What kind of measures do we put in place to detect these faults? Remember, some of these faults we just simply can't exclude, so we need to detect them if they occur. How reliable are these measures and how do they translate into our diagnostic coverage? Once again, the standards give us some guidance. These tables are partially extracted from AS 4024 Part 1503 Annex E, which is used as an informative estimate for DC and provides some examples of what level of DC to expect from certain fault monitoring practices. So for input devices like our interlock switches, presence sensing and e-stop devices, etc., there's several things we can do to achieve a medium or high level of DC. Cyclic testing stimulus by dynamic change of the input signals. It's a fancy set of words. We saw this in our interlock switches session where the machine is not allowed to start up until the guard is opened and then closed. What this does is cycle the inputs on, off, and on again to ensure that all the contacts are working correctly. This is done to detect any failures before the machine can be restarted. But this test is limited as it only detects the faults at the moment we decide to test them. If we test too infrequently, or there are maybe several guards in series which can mask some faults, there's a chance that some faults are not detected when we cycle the inputs or between tests. So this fault monitoring measure only nets us 90% DC. We could do this for when we need a DC of medium, but it's not enough for a DC of high. We could do a plausibility check, which is another measure described in our interlock switch session. This requires the use of diverse actuation methods to ensure that a single fault is detected and is a good measure to reduce common cause failure. This is where both devices fail in the same way at the same time. For example, using a mix of normally open and normally closed mechanically linked contacts, our safety control system could monitor the status of these diverse inputs and make sure that they both switch appropriately at the same time. This is a good method of fault detection, which could give us a DC of up to 99% as required. Some detection methods are more practical for some devices than others. For example, we may be using multiple I/O into the one safety control circuit, where we will need to detect static faults and short circuits, which may not be discoverable until the next demand. This is where we get cross-monitoring of input signals at regular intervals by the control system. This uses time-based software logic to monitor the signals for their integrity. It ensures that static faults are detected before the next demand. There are measures which can be used to detect faults within the logic devices themselves, which run the gamut from low to high DC. The logic devices could perform self-checks on the software, including watchdog and plausibility, by running several instances of the program operating under diverse methods, or on diverse hardware and comparing the outputs. The objective here is to detect a defective program sequence, which may exist if the individual elements of the program responsible for the safety function are processed maybe in the wrong sequence or period of time, or maybe if the clock of the processor is faulty. This could be done by self-test by the software, and this could net us up to 90% DC. This could also be done by coded processing, where the processing units are designed with special fault detection or fault correcting techniques, which can detect faults very early on. This could get us up to 99% DC as required, depending on the techniques used. And we can also use several measures to detect a fault in the final elements of our safety control system, the output devices. Again, things like cross-monitoring of output signals using software logic to detect shorts, but also indirect and direct monitoring of the output devices themselves. Indirect monitoring could be the monitoring of the consequence of the output device being in one state or another. For example, you could monitor the status of a valve by measuring the pressure or flow rate which the valve is controlling. If the flow rate is more than 0, it can be inferred that the valve is not closed sufficiently and may have failed. This can give us between 90 and 99% DC depending on the application. Or, one of the most effective measures is direct monitoring, where we're monitoring the status of the output device itself. This could be measuring the actual position of a control valve, ensuring it's opened or closed within the correct limits, or very commonly for electromechanical devices, using mechanically linked contacts to determine whether the main contacts have opened or closed as expected. This can give us 99% DC needed for high-risk applications, and it's a very common fault detection measure. This is where safety monitoring relays become incredibly useful, as they are specifically designed and engineered to perform the fault monitoring task we so critically require in our safety control systems. Safety monitoring relays take care of all the diagnostics and go to the safe state in the event that a fault is detected. In a typical and simple safety control system, some of the faults which can be detected are when one of the input signals fails to open or close, depending on the actuation method. If a short circuit occurs between conductors of the input device, that is, maybe shorts to 24 volts, 0 volts, or even shorts between the two safety signals themselves. If one of the output devices fails to open, like a stuck contact on the main contactors. If requiring a manual reset, they can detect if the reset button is being held down manually from deliberate misuse or a wiring fault. And of course, detect internal faults within itself using some of the logic fault measures we saw in the earlier examples for estimating DC. In fact, all of these faults are realizations of some of the measures used in the examples provided in the standards, and can be used to detect a high proportion of faults which can't be excluded. This is exactly what we need in our safety control system to satisfy our DC requirements. The way many of the wiring faults are detected is by using dynamic test pulses on the signals to and from the external safety devices. This is done by pulsating the signal in a very specific pattern, which is unique to that particular safety channel signal. The safety monitoring relay is monitoring the signal, and it must see the expected pattern. If the conductor carrying this unique signal comes into contact with a solid voltage, like a 24 volt supply, it will hold the signal high at 24 volts. If the safety monitoring relay detects this as an invalid signal pattern, it then trips as a fault has been detected. Likewise, if the conductor comes into contact with 0 volts, the signal will be held low. Again, an invalid pattern is detected and the safety monitoring relay trips. For high-risk applications, we're likely going to be using redundant control signals. So the test patterns between the two channels can be made unique to each other so that if they ever come in contact, both signals will mix and become an invalid pattern. The safety monitoring relay detects this and trips as a cross-channel short fault has occurred. Test pulses can be used on input devices, but also on output devices. So if, for example, a short to the main supply occurs on the safety output to a contactor, it could be held in the energized position if the safety monitoring relay ever trips, and we won't be able to detect this fault until it trips and we attempt to reset it. So by monitoring the output voltage with test pulses, we can detect a short as it occurs and trip the safety control system as soon as possible to reduce the likelihood of another fault accumulating. The test pulses produced on the output are also very quick, on the order of microseconds, so they don't largely affect the performance of electromechanical switching devices like contactor coils. They happen so quickly that the coil will remain energized and they don't buzz. This method of fault monitoring using test pulses is one which can provide us with over 99% diagnostic coverage. Safety monitoring relays also have the facility for direct monitoring of the output devices via mechanically linked contacts. The contacts of the output devices are connected in series with the reset circuit or a special feedback monitoring loop. If any one of these output devices fails to change state, like the contacts being stuck in the closed or energized position, its respective auxiliary contact is prevented from closing, leaving the loop disconnected. When this happens, the safety monitoring relay is prevented from restarting, and thus the machine is prevented from starting up again. This should prompt the operator to check the output devices to identify which one has failed and replace or repair it before the machine can be started again. This method of fault monitoring is a form of direct monitoring and provides us with up to or over 99% diagnostic coverage. Whenever the safety control system is tripped, it needs to be reset. This can be done automatically or manually, depending on the risk assessment. Safety monitoring relays generally come in one of or both of these reset modes. In AM mode or auto manual, the reset is performed by simply applying a high signal to the reset input of the safety monitoring relay. This can be done manually by using a reset button or external contacts to apply the signal, or it can be done automatically by hardwiring the source of the input signal directly into the reset terminal. This is usually 24 volts. What this mode does under the hood is look to see if the signal on the reset input is high, and if it is high, then it will reset. If your risk assessment deems that a manual reset is required, this mode may not be the best to use, as it can be easily defeated by taping down the reset button, so the signal is always high. Where a manual reset is required by the risk assessment, it's best to use a monitored manual or MM mode. What this does is monitor the dynamic change in the reset signal to ensure that the reset signal is not held high due to a fault or through misuse. The safety monitoring relay achieves this by looking for a rising and falling edge of the reset signal, and the time between edges is between a prescribed time period. The timing is generally at least 250 milliseconds, which prevents accidental reset due to contact bounce or vibration, and is no more than 3 seconds to ensure that the button is not being held down or a short has occurred. The consequence of using this method is that it's very hard to defeat and is the recommended practice in the standards where a manual reset is required. The role of safety monitoring relays is not only just to perform fault monitoring and diagnostics, but to perform some actual logic to make the safety control system functional in the first place. As such, there are various different safety monitoring relays which can be used to perform one or many of the typical safety functions found in machine safety applications. The most common and simplest is the discrete on-off functionality. This replicates the conditions of a simple relay where you energize the input and the output is energized, de-energize the input and the output is de-energized. Basic discrete logic. While this is the most straightforward functionality, it's used in an overwhelming majority of machine safety applications and covers many prescribed safety functions, including interlocking, manual reset, hold to run, prevention of unexpected startup, and emergency stop. As they are used for most safety applications, the input types which can be accepted need to be as open as possible. Safety monitoring relays will generally accept a wide variety of input types, which are found almost universally in machine safety applications, hence universal safety inputs. Input devices which utilize volt-free contacts are accepted either by using special pulse-tested outputs from the safety monitoring relay, but they could also use a solid 24-volt DC signal. In redundant two-channel systems, this would be used with two normally closed contacts, but some legacy systems may use a combination of normally open and normally closed, which may not be accepted by some safety monitoring relays. Alternatively, if using single channel architecture, a single contact can be monitored and provided with its own pulse tested output. Solid state devices which use OSSD signals can also be wired directly into the safety inputs. OSSD stands for Output Signal Switching Device, which is generally a 24-volt DC PNP output from a safety device like light curtains or scanners or some non-contact interlock switches, which incorporate their own pulse-tested signal instead of the one provided by the safety monitoring relay. Safety mats and other pressure-sensitive contact devices may also be wired into most safety monitoring relay inputs. However, these are done a bit differently. In this case, the two pulse-tested signals are wired into their opposing inputs. What this does is tell the safety monitoring relay that if it detects a cross-channel short, it will trip the outputs, but it won't register as a fault, rather a demand. This is because of the nature of safety mats, where we want a cross-channel short to occur if we step on it. However, as we are effectively disabling cross-channel short detection as a fault, if a real wiring fault were to occur, it would not be detected, thus reduces our DC capabilities. So safety mats are only valid for up to category 3 PLD. Two-hand control is another type of discrete functionality offered by some safety monitoring relays. However, it requires a little bit more logic to pull off. This is used in manual loading and unloading applications where the operator's hands need to enter the machine to perform a task. In order to keep their hands out of the way while the machine performs a hazardous process, two push buttons are needed to be pressed together within a specified time in order to enable the machine to function. These buttons need to be located far back from the hazard and also need to be specifically guarded and spaced apart from each other to ensure they can't be defeated. For example, by pressing one's hand and elbow on both operators at the same time while the other hand is free to enter the machine. The safety monitoring relay is now also responsible for ensuring that both button signals are operated and remain operated at near the same time, so is checking the plausibility as well as performing time-based control. Safety monitoring relays can also perform guard locking functions and are used in conjunction with guard locking interlock switches. These applications require that the guard remain closed during the hazardous portion of the machine process and only unlock once the hazard has been removed. When stopping a machine with a long rundown time, it's pertinent to know when the machine has slowed down to a safe state before granting access. For machines which have a predictable rundown time, this can be achieved using a predetermined time delay. In this case, the safety monitoring relay is provided with an unlock request input. When this is pressed, it de-energizes its dedicated outputs, which in this example de-energize the contactors supplying power to the machine, and performs an uncontrolled stop. In some modes, these outputs could be used instead to issue a stop command to something like a VSD or a drive and perform a controlled stop before isolating power. In either case, once the stop command is issued, an internal time delay is performed by the safety relay. Once the time has elapsed, which is selected in conjunction with the expected rundown time, an unlock signal is automatically sent to the guard locking interlocking device, which then unlocks the guard, and it can be safely opened with the machine completely isolated. The safety monitoring relay is also monitoring the status of the interlock device, ensuring that the machine cannot be restarted while the guard is open. When the guard is then closed, the manual reset command can be given, which prompts the safety monitoring relay to remove the unlock signal from the interlock switch, and then checks its status to ensure that the guard is closed and locked before re-energizing outputs. This relies on a time delay to ensure that the machine has reached standstill. However, if the machine does not have a predictable rundown time, more direct means of ensuring a safe speed reached is required. So some safety monitoring relays can also provide a safe speed monitoring function, which can be used for guard locking applications to ensure that the machine has come to standstill or at least a safe speed before granting access. The functionality between it and the time delay variant is that it uses direct monitoring of the motion of the machine to determine the speed and only unlock the guard once the safe speed has been reached. In this example, speed is measured by utilizing two proximity sensors, which detect a notch, keyway, or something similar directly on the moving load. The safety monitoring relay measures the time between pulses of the sensors to determine how fast the load is moving. Two sensors are used for redundancy purposes, and they are also arranged such that at least one of the two sensors is detecting the load at any one time. This is done also for fault monitoring purposes. If one of the sensors fails or is removed from the load, the signal will go low. If the safety monitoring relay is expecting at least one signal to be high at any given time, by the time the second sensor detects the notch, both signals will have gone low, and thus the safety monitoring relay trips on an input fault. Safe speed monitoring can also be achieved through other means, both directly and indirectly. Some high-end safety monitoring relays are capable of using one or more encoders to directly monitor the speed of the load. However, given the nature of encoders, they can also be used for additional motion-based safety parameters, whereas the use of proxy sensors will typically only provide the speed. In some more advanced motion applications, the safety of the machine may also be ensured by limiting to a safe speed, acceleration, deceleration, position, or even direction. Encoders are especially useful in these applications and so lend themselves well to motion-based safety functions. Another method in monitoring speed is by taking advantage of the intrinsic nature of an induction motor when it's allowed to spin freely. Motors can behave and literally become generators when electrical supply is removed and it is kept in motion through the load, generally via inertia. When the motor is freely spinning, it generates a back EMF, or electromotive force, which is realized as a voltage on the motor supply terminals. So by measuring the voltage and frequency on these terminals, we can infer whether the motor is moving or has reached standstill. Specialized safety monitoring relays can tap into the supply conductors of the motor and monitor the back EMF voltage and frequency. And it can be used in conjunction with other devices to perform the guard locking safety function. So ensuring that the guard can only be unlocked and open when the load has come to standstill. In other words, when the back EMF voltage and frequency has dropped to 0 or a lower threshold. Safety monitoring relays do not necessarily have to operate in isolation. Rather, they can be linked together with others to perform additional logic or be provided with additional input and output. The current generation of safety monitoring relays can be linked together by a single wire, which carries a unique pulse-tested signal. This is called SWS, or single wire safety. The pulse testing is there to ensure that a short circuit fault is detected. The SWS signal, while it is pulse tested, is still discrete in operation, so it's either logically on or off. However, this is all that you need in order to link multiple safety relays together. Where this feature becomes most useful is in larger machines which require additional I/O, which is otherwise afforded by a single safety monitoring relay. So SWS can be used to link several together to expand the I/O count. Furthermore, it can be used for zoning and segregation of the safety functions of a large machine, so that only certain areas of the machine are shut off during specific safety demands. For example, in the slide here, we have a machine with multiple guarded access points, Zone 1 and Zone 2. If we want to enter Zone 1, we don't necessarily need to shut off the whole machine, only the area which we want to access. Yet at the same time, we wish to have a global emergency stop operator, which can be used to shut down the entire machine at once. So notice from the example, we can trip either Zone 1 or Zone 2 separately without affecting the rest of the machine. Zone 2 is even using an expansion module to extend the number of outputs. However, if we press the global E-stop, both zones are shut down simultaneously. This is the power of linking together multiple safety monitoring relays using single wire safety. Safety monitoring relays do not necessarily mean plain and simple standalone devices either. Modern day technology allows these devices to integrate into industrial networks over common Ethernet IP. This allows diagnostic data to flow into standard non-safety processes. We can use this information for analytics with real-time data, which can be used either immediately or over a fixed length of time to help provide the plant owner with a better idea on the operation of their machine. This can give them the ability to make better operational decisions and optimize their processes, and can also be used to prompt preventative maintenance down to individual devices which make up the safety system. It can also be used to increase non-safety diagnostics, which allows us to gain as much information as possible from individual field devices. The level of diagnostics no longer only just points to where on the machine a problem exists, but has increased to the point of providing detailed fault codes and suggested remedies. Ultimately, the non-safety communications and diagnostics can help minimize unplanned downtime and increase overall efficiency, all from a smart safety monitoring relay. And so concludes today's presentation on safety monitoring relays. By now, you should have some more intimate knowledge on the function of various types of safety monitoring relays, their applications, and some of the special requirements with respect to the machine safety standards. For more information on the selection or even just on machine safety in general, there is a wealth of information available in the NHP Machine Safety Selection Guide. I also highly recommend reading through the Rockwell Automation Machinery Safe Book 5, which is a bit more advanced, but provides fantastic guidance around designing and navigating machine safety control systems. I'm now able to answer any questions you may have sent through during the presentation that haven't already been answered by our expert moderators.
Hi, Daniel. It's Thomas from NHP here.
Hi, Tom.
Thanks for the presentation so far. So we're just, as you said, open to questions. So we've answered most of the ones that came through. We'll just give it a moment before to wait for some more questions. So, okay, we have one here. So they've written, I've heard somewhere that electronics can't be used in category 1 circuits, something about it not being applicable to well-tried components. If that's the case, can something like a GSR relay be used since it's electronic?
That's actually a very good question and is currently under discussion by the international safety committees. So you're correct. There is a clause in the standards which state that a well-tried component or a complex device that uses a microprocessor or an ASIC or even a PLC is not a well-tried component. But for category 1, you don't necessarily need to have a logic device in there as long as you're using well-tried components. So, for example, an emergency stop or a limit switch and the safety contactor, just the two. You can still use the safety monitoring relay for diagnostic purposes, but it's not actually required for category 1. There is no diagnostics. But you definitely can still do it. In fact, by using the safety monitoring relay, you're effectively designing a category 2 system. But that's a very, very interesting question, but I'm sure we'll get some more clarity around the term well-tried component probably a little bit later in the year when the International Standards Organization work through that particular clause. Great question, thank you.
Okay, thanks for that, Daniel. So we have another one here from Jake. So he says, your examples show contactors. Is it possible to achieve the required DC with an air circuit breaker? So for example, a 10 power 2.
It is possible. A little bit of calculation is required though. So with circuit breakers, they are technically a well-tried component, that they are listed as such. But what you need to do is you need to work out whether or not the number of operations of your breaker is enough to last the expected lifetime of the machine. But what you need to ensure is that you are monitoring the status of that breaker. So you need to have some direct feedback. So that would be monitoring with auxiliaries to ensure that the breaker has opened and closed as required. That will get you your diagnostic coverage. The only thing though with circuit breakers is that they aren't necessarily designed for many operations for switching loads. They're mainly there as protective devices. So you'll probably find that they will need to be, suppose, tested regularly to ensure that they're still working. But yes, you can definitely use circuit breakers as output devices and monitored by safety relays.
Okay, thanks for that, Daniel. Another one here. So for GSR used with devices like safety mats and bump strips, how does the GSR device monitor the inputs, which are normally open?
Okay, this one requires a little bit of fancy wiring. So traditionally with bump strips or safe edges, you needed to have a terminating resistor, which effectively makes it a normally closed system. You don't need to do that anymore. So what you can do instead is you wire up the two sections of the bump strip so that, how do I probably explain this easily? The outer section of the bump strip, which you come in contact, is effectively already a closed contact. The internal part of the bump strip is another closed contact. So they're effectively already normally closed. But what the GSR is doing is it's waiting to see a cross-channel short. So the GSR, or the safety monitoring relay, is sending a pulse-tested signal through both contacts, in quotation marks. And then when you press onto the bump strip or the safety mat, the two contacts or the two conductive parts make contact. And what this does is it mixes up the test pulse signals, and then this is detected by the safety relay as a cross-channel fault, and thus it actually trips the safety relay. You do need to be careful when wiring these up because, as I mentioned earlier in the presentation, you need to make sure that your safety relay is configured for this particular mode, because what you don't want to happen is you stand on the mat and the safety relay faults, and then it faults in a way that you have to cycle the inputs, but you can't actually cycle the inputs because they're hardwired in. So that's why a lot of safety relays have a mode which disables cross-channel fault detection. It will detect the cross-channel short, but it doesn't actually register as a fault. Instead, it just comes up as a demand. So it still trips the relay, just it doesn't come up as a fault per se. Another good question, thank you.
Okay. Next one is, what is the difference between a safety relay and a normal relay?
So a safety relay generally is used with forcibly guided or mechanically linked contacts. This is so that you can actually monitor the contacts. General purpose relays aren't really suited for this function, because if you imagine one of the contacts gets stuck, the other contacts that are in the same relay you can't necessarily prove that they should be in one state or the other, because there's no mechanical linkage between them. So in safety relays, they have that mechanical linkage. So if one contact is stuck in any position, the other contacts are also held in a position that you can use to basically ensure that the contacts are in one position or another. The other thing with safety related components is that there will be safety data associated with it. And you use this data to calculate your mean time to failure. General purpose relays often don't come with this data, and you need to do a little bit of digging through specification sheets and to come up with a value. But generally speaking, with safety relays, a lot of this data is already provided for you. But really the main distinction is those forcibly guided or mechanically linked contacts.
Okay, thanks for that. Another one here. So are any of the safety relays compatible with IS barriers for use with simple devices in hazardous areas?
They can be used, but not directly connected. So with IS or intrinsically safe, we're talking about EXI for explosive atmospheres. So for simple apparatus like safety mats or emergency stop contacts or limit switches, you can't directly wire them into the safety relay, because you need to have a barrier in there to provide the energy limiting for intrinsically safe. This question sort of goes a little bit out on a tangent, but what you can do is you can use the barrier, the intrinsically safe barrier, in between the field device and the safety monitoring relay. The only thing you need to be careful of is any wiring faults that might occur in the field. If you pick a intrinsically safe barrier that can either pass through those test pulses, like a Zener barrier, that will work. Or if you're using an isolation barrier, you need to make sure that that barrier has its own fault detection capabilities. And that usually uses line resistors on the end of the wiring. So if you get an open circuit or a short circuit fault in the intrinsically safe wiring, the barrier itself is what detects it. And you tend to find that a lot of isolation barriers are used in the process world. They have SIL ratings or safety ratings already associated with them. So they're definitely really, really good to use in safety control systems. Very good question, thanks.
Okay, thank you. Next one here, and probably the last one. Can the single wire link be used for category 3 or category 4 systems?
Yes, to both. So the single wire link, it is a single wire. However, it uses that test pulse pattern to detect for faults. What you generally need to do with category 3 and category 4 is to have redundant input and output devices. The whole point with category 3 and 4 is that a single fault doesn't lead to the loss of safety. What kind of fault could you get on that single wire link? Well, if you think about it, either you lose connection, in which case everything turns off, that's one fault. You might have a short circuit to 24 volts or to another conductor. Again, it's using that test pulse pattern. So if one of the, if the test pulse pattern is held high or low, or it's garbled with another signal, the safety relays detect this as a fault and then will trip. You tend to find that with redundant systems, it's mainly attributed to the contact sets. So in a limit switch or an e-stop, you'll have two contacts. The idea with your two channels is that if one contact remains closed, the other one still opens. There's no mechanical switching going on with that single wire safety loop. So that kind of fault doesn't exist, in other words. But yes, you can use the single wire safety link for category 3 and category 4 applications, no problem.
Okay, thanks for that, Daniel. And I think that's all we have time for today. So thank you for your presentation.
Excellent. Thanks, Tom, and thanks everyone for the questions. Again, thank you very much for joining us for this webinar. I hope you found it beneficial, and if you'd like to watch it again, a recording will be uploaded to the NHP YouTube channel shortly. So to find more webinars in this series, you can go to our nhp.com.au website or dedicated NHP YouTube channel. And if you have any further questions about machine safety products and solutions, please contact your local NHP sales representative. With smarter and faster decision-making and seamless connectivity spurring new collaboration, NHP is enabling the connected enterprise. Thank you again, and I'll see you next time.